So this is what we call now an implicit function. So given x, so when we are solving our ODEs in this class, we usually say, okay, given my u, I can evaluate du dt, right? Once I have a function that gives u, I can compute du dt. I can use either ODE45 or any of the method we discussed here to solve the equation. Here, do we satisfy the criterion if we have this equation and A is known, rho C is known? Given x, can we compute dx dt? Basically, yes. How? It's a function, but like you can, so you know the analytical form of this and this, but like without knowing what dx dt is, how do you compute the value of the function? Newton's method again, right? So this is what we call an implicit function, right? So instead of having a function being explicitly defined using a formula, this is the same type of problem we encounter when we are solving an implicit time stepping, right? Do you agree here?
Some kind of problem where you have to know the step.
Yeah, we have to know this in order to compute this to get this.
Yes.
Right? It's the same type of problem. And the solution is the same. Right? So for example, here you are doing time stepping, right? So you probably starts by knowing what is the dx dt at the last time step.
Yep.
So if you know what is dx dt at the last time step, you can use that as an initial guess. So again, I can say, okay, what if I approximate this using a times rho c times k n of x dx dt at last time step, okay? Plus a times, oh, you have nth power, right?
Yeah.
But then anyway, you can linearize this whole function, right? The linearized function is probably going to be a times n times rho c to the n minus 1th power. That's the derivative of this function. And using chain rule, familiar with chain rule, you have partial rho c, partial dx dt, right? Times what? Dx dt n plus 1 minus dx dt n, right? That's my first order Taylor series approximation for the value of this function at n plus 1. So let's say n plus 1. All right. Or I think it's probably easier to say this at n is equal to this. I think I mixed the use of n. So let's use m as my time step.
Yeah,
all right.
Sorry.
So this is m minus 1. This is m minus 1. Does it make sense? I'm basically Taylor series expanding this function around this unknown function. All right. So
and this
what
gets you better accuracy then than just using the previous time step because you have the derivative.
Yes.
Here.
Yes. Then basically you move this unknown into the left hand side and solve this equation, right? And this gives you a better estimate of dx dt than just using the previous time steps dx dt. But then you can go into this loop again, right? You can now expand the right hand side, not on the old value, but on the better guess of what is your current dx dt, and do this again. So basically using Newton's method to solve dx dt once you are given the value of x. Right, so basically that gives you an implicit function of dx dt as a function of x. So that means if you code up a ODE solver with ODE45, your function f actually have to involve an iteration, involves the Newton's method of solving what is dx dt given x, and return your dx dt to ODE45 or whatever.
Mm-hmm.
Right?
I ran into that problem.
Okay. And what was your solution?
I tried to write my own ODE solver.
I see.
Bad news.
Yeah.
That's why I'm in this class.
Okay. Yeah. For this one, I think I'm not depending on what's your function of this and this. If these are pretty reasonable functions, the system should not be very stiff.
Yeah, I wrote the functions out over here. So kn is just pi x squared L, and pc is just a bunch of knowns and kn.
Bunch of knowns and
Yeah, so pc is the burning area times the A value of the propellant times the density of the propellant times the characteristic velocity of the propellant, all to the 1 over
okay.
1 minus n power.
what is n?
N is the same n as before, the burn rate exponent.
How
the
big is it usually?
What?
How big is n?
Like 0.4?
Oh, it's fine. And you shouldn't have a very stiff system. Should be fine.
So how does PC depend on dx dt?
Because
I
that
think
kn term.
This guy.
So the kn term written up above pc is pi x squared L. So the x coordinate changes on every time
No, I
step.
think he's asking how does it depend on dx dt.
Oh
I
yeah.
think that's your C star, right? What's your burn rate?
No, the PC just plugs into.
Just only uses k.
Yeah. So sorry. So I've written it twice. So you notice that PC actually contains the burn rate formula in it. So the formula for dx dt that we solved up there, the dx dt equals a pc to the n, is actually in PC.
Oh, okay.
Okay,
So
so,
you
it
could-
could have been.
I could have factored that and had
So this is the same as this, right?
no. That's a row C, not a
Oh.
PC.
Oh,
Wait,
okay.
wait. PC is. But wait, which factors factor out into dx dt?
It's not
You
clear.
could move the A to the other side. You've already got the PC and then the N to the other side.
Oh, gotcha.
No, but like if PC only depends on x, if you just don't look at the differential equation, you just look PC is equal to some function of x times a bunch of
Yeah.
constants. Let's see any change.
What is C star?
C star is a constant based upon the propellant you have.
Then I don't see where
Yeah,
it depends
should
on
be-
dx dt.
Yeah, it should only be. Yeah.
Yeah, if that's the formula, then given x, you can just compute the whole PC, right?
As long as kn is the only thing that moves out of kn a row c and or row and c star. I think that's right.
So I guess the reason I think it depends on dx dt is I think in the version of that formula I wrote, I substituted n for dx dt.
Oh wait, n is also a variable.
Yeah. So n. So.
Oh right, yeah.
Yeah. So you can do you can multiply both sides by like 1 plus n and then move the a over, and then you essentially get a pc to the n equals kn row c star to some function, which could then be written as dx dt equals.
What is
Okay.
n?
N is a empirically determined coefficient that just like sets the.
So it's a constant.
Yeah.
Anyway, I think in this formula you already solved analytically the implicit formula.
I might have done that.
Probably
I
have.
don't know.
Yeah.
So yeah, so in general, if I think if you go towards a more complex formula, maybe you won't be able to do that, right? And if that's the case, then just do whatever that is here. Usually that's usually the case when you have an equation that is make a lot of assumptions simple enough. You can use analytical method to solve it. And once you start to remove the assumptions, the equation gets more complicated, and at some point, analytical method is going to fail, and you have to switch to numerical method. Be it solving differential equations or solving system of nonlinear equations or just a single nonlinear equation. Right? So here, you probably analytically solve some nonlinear equation to get an explicit formula. When you go to a more complex formulation, you may have to use Newton's method to solve it. All right, so let me expand on this a little bit more. So this is actually a kind of representative problem. Here you have some kind of a slow reaction going on, that is burning of the propellant, and also the gas dynamics that here determines your pressure, right? So here, what's your name again?
Charlie.
What Charlie used is basically a algebraic equation that links the pressure to the burn rate. And the assumption here is the gas dynamics goes infinitely fast, right? And sometimes if that assumption cannot be assumed anymore, you may have to also simulate the gas dynamics. And if that's the case, you have a stiff system to deal with, because the gas dynamics is usually a lot faster than whatever the speed of the propellant is burning, right? So that's one way you can get into stiff systems, by starting to incorporate more physics or make less assumptions. All right. Okay. What time is it? Oh, already 4 o'clock. Okay. So that concludes our discussion of our ODE, and we'll start to look at partial differential equations starting next week. All right.
That's so cool.